So we're just beginning our new unit on acids and bases. Now, you are actually familiar with some acids and bases just from what you've had around the house. For example, if you've ever had vinegar on your salad, you are familiar with an acid, and you know it tastes kind of sour, and you know if you get vinegar into a cut on your fingers that it would sting, and those things are characteristic of all acids. Orange juice is a little bit sour, lemon juice is very sour, and that's because they have acids in them. So they're just watery materials, but if they get concentrated enough, they can be dangerous. But these kinds of things like orange juice and lemon juice and vinegar are not very dangerous, but they're still acids. And then, so characteristics of acids are that they're kind of watery, they taste sour, and also they have some chemical properties. If you test them with litmus paper, they will turn the litmus paper red. If you put phenolphthalein in them, they will not turn the phenolphthalein colored. It will just stay clear. Now, bases you're also familiar with for a few things that you might have seen around the house. For example, soap. Soap is a base, and it feels slippery. We would just call it feeling soapy. But that's a characteristic of all bases. They feel that way. Now, a lot of bases you wouldn't really want to be feeling because they would be too strong and they would pull the skin right off your hands. But if you were to feel them, they would feel that way. Now, bleach, for example, it's not really very safe to get that on your hands for very long because that's fairly strong. But you would feel that also slippery, kind of like soap, because bases are like that. So bases feel slippery. If you were to taste them, they would taste bitter. I don't recommend that you taste them, but they would taste bitter. And sometimes foods are bitter because of the basic substances that are in them. Bases would turn litmus paper blue. Bases will turn phenolphthalein pink. So those are some of the characteristics. Now, as far as really strong and concentrated acids and bases, if you were to get inside of the battery of the car in your garage, you would find a really strong acid there. That's called sulfuric acid. And it's a strong acid and it's a concentrated acid. And those are two different things, and we'll get to those a little bit later in this unit. But either one of those will increase the strength of the acid and make it more dangerous. Drano, if you have ever used Drano at home or your mom or dad has used it in the sink, you might have seen what happens when that goes down the drain. All of a sudden you see like boiling and steam coming out, and that's because Drano is a very strong base, and when it reacts with the water, it makes the water so hot that it actually can start to boil and steam like that. So that's, again, something that you wouldn't want to get your hands into or have it splash in your face or anything like that. Now, chemically, what happens is with an acid, just by definition, an acid is something that when you put it in water, it increases the amount of hydrogen ion. So an acid, by definition, increases the amount of hydrogen ions in the water. When we talk about acids and bases, almost always we're talking about water solutions, and certainly this year for us, that's what we'll be talking about. Bases increases the amount of hydroxide ions in the solution. So there are lots of different substances that when you dissolve them in water, they will produce either hydrogen ions, and that makes it an acid, or hydroxide ions, and that makes it a base. And you might notice that if you were to put these two things together, you would make water, because a hydrogen combined with a hydroxide will make water. And that's why when you add an acid and a base together, they can neutralize each other, because they will actually react with each other and form a bond between these two things, which gives you a water molecule, which is neither acidic nor basic. So that brings us to the next topic, which is that of the pH scale. The pH scale measures how strong of an acid or base we have. And you might have seen this before and be aware of the fact that 7 is a neutral pH. And these, by the way, have no units. We don't see numbers very often that don't have units, in science anyway. But these numbers don't have units. So a pH of 7 means it's neutral. And if we go all the way to 14, which is the highest pH we can get, anything in this range is a base. Now, this can go all the way down to 0, and anything in this range is an acid. So obviously the things at the two ends would represent the strongest acids and bases, and something close to 7 would represent something that's maybe weaker and not as hazardous to your health. Now, we won't actually learn the math that goes with pH this year, because in order to do that we need to know about logarithms, and that's something that you probably haven't learned yet. I think it comes either late Algebra 2 or early pre-calc, something like that. So you'll have to take my word for the fact that when you go one unit, one direction or the other, you're actually changing the concentration of either your hydroxide, well actually you're changing the concentration of both hydroxide and hydrogen ions by a factor of 10. So if we go from 7 to 6, it's 10 times more acidic. Going from 6 to 5 makes it another 10 times more acidic, and so forth. And if we're going in this direction, going from 9 to 10 becomes 10 times more acidic. Going from 10 to 11 makes it another 10 times more basic. Sorry, I meant to say basic, going in that direction. So for this year, we just look at the scale and understand that this end is acidic and this end is basic, and we won't do any of the math associated with that. Now, one other thing I would like you to be able to do with acids and bases is to show what happens when we put these substances into water. So I want to teach you how to write a dissociation equation. And I'm going to do it in a generic form, and you'll be practicing this in your homework. But let's say we have an acid, and in a generic form we'll call it HA. And we're going to put the H on there because all acids have a hydrogen ion that will dissociate. It will break away from the rest of the molecule when it gets into water. Now, as far as a state, I'm just going to write a question mark because sometimes they're solids, sometimes they're liquids, sometimes they're gases. We don't know. Since this is a generic one, we'll just call it HA with a question mark. On the other side of the equation, remember that this reaction represents what happens when you put this in water. So we've already learned what the state is going to be. It's going to be aqueous. That's what it means to dissolve something in water. It becomes aqueous. Now we also know right off the bat that if we have an acid, it's going to produce a hydrogen ion. So before we even have to think very hard, we can write down H plus aqueous. By definition, that's what happens with an acid. Then we stop and think, okay, what's my other product? So we just look at what's left. What's left when I take the hydrogen off? Well, it would be A. And I think I better get something that I can minus. And I know it's minus because I took a positive hydrogen off, and this didn't have a charge to begin with, so I'm going to need a plus and a minus over here. And this is going to be designated AQ also. So when you write these, even if you get confused at first because maybe it's a molecule you haven't seen before, just think to yourself, all right, it's an acid, I'm going to take a hydrogen off, H plus, and it's aqueous, and then just look at whatever you have left and add the negative sign, and that will also be aqueous. So here it is in generic form. Now for the base, because I want to talk about strong bases today, and I think I can say that all the strong bases have an actual hydroxide ion attached to them. You'll see that when we get to weak bases, they don't always have the hydroxide ion that's obvious right away, but that's a story for another day. And again, most of these are solids, so I'll just put a solid there, but some could be liquids or gases. But most of these are going to be solids. So I'm using B just to represent base, and I'll stick the OH on there because they're all going to have an OH on them. So when we take it apart, we'll have, I'm just going to write the OH first because I know by definition if this is a base, it's going to put hydroxides into solution. And the whole point of saying what happens when you dissolve it in water is to make it aqueous. So we've got to have aqueous over here. So what's left after I take the OH off? Well, that would be a B. And I know it's going to be plus, and I know that's going to be aqueous also. So now I have a plus and a minus that will cancel to get back to the original compound. Now occasionally you might have something like, maybe there's going to be 2 hydroxides here. So that might happen, for example, if you have calcium hydroxide or magnesium hydroxide, something that's got a +2 charge. I know this is taking you all the way back to something we did quite some time ago, so this is a really good review for us. But if that were to happen, then I would have 2 hydroxides like that. So notice that I'm not putting it over here as a subscript. I'm saying, no, there's 2 hydroxides. So over here they get represented as 2 hydroxides, 2 completely independent little entities. And then that would end up giving this a 2+ charge, because that's why we had to have 2 hydroxides, was because that had a 2+ charge. The same thing could happen with your acid. You could have an H2, which would require 2 hydrogens over here. But normally, if we're just talking about strong acids, it's only the first hydrogen that comes off anyway. So usually you don't have to worry about that. But that is how you write a dissociation equation.